let's continue. Something? No. Then let's continue. So the topic today is the n-variate or the multivariate Gaussian distribution. And that's actually a fairly big topic, like everything. And the reason why we are looking at that is because we are still in the process of formulating our GLM, or your GLM, or my GLM, I don't know. We discussed this bit, so the matrix multiplication early on. And I told you last time and maybe the week before, so we looked into probability theory for a couple of times now, that this is about this stochastic part of the GLM. And really what's behind this stochastic part of the GLM is the fact that these error terms are distributed according to a multivariate Gaussian distribution with a specific expectation vector and a specific covariance matrix. And to explain that, we of course need to talk about n-variate Gaussian distributions. Or multivariate Gaussian distributions. And of course the univariate or one-dimensional Gaussian distribution that you're familiar with and that we briefly looked at last time, so this bell-shaped curve, is a special case of that. So it's not like different things now, it's just a generalization of something that you have encountered previously. Yeah, so the way we are going to do that is that first I basically now write down the multivariate Gaussian probability density function. So we discussed last time what probability density functions are. And then we have a close look at this multivariate Gaussian probability density function. So we will clarify a number of concepts that go in there. So let me first do that. So I do it as follows. So the let's get rid of that and call this multivariate Gaussian. It's also called normal distribution, by the way. It's the same thing, so don't get confused. So that's the multivariate Gaussian PDF. So it's a probability density function, and I might write it like this. So we have this function f that depends on these two things here, mu and sigma. And what this function takes as input are n-dimensional real vectors, which are mapped onto real values larger than 0. And it takes such inputs and maps it onto the values that it takes on. And these values are defined as this, what I'm writing here is nx semicolon mu sigma. And this expression here, so this nx mu sigma, that is defined as 2 pi to the power of minus n half this thing here, and this thing here. Yeah. So that's the multivariate Gaussian probability density function, and the aim then is to have so of course it describes kind of a probability distribution, and we will discuss its intuition, of course, also later on, specifically when we talk about bivariate and also univariate special cases of this. For now, because we will also have to manipulate this, I want to use this as a vehicle to discuss some other aspects that we will need continuously, and which will would fall a little bit more into the math preliminaries section, but we haven't covered them. So I will basically now give you a closer outline of what we're going to talk about, so, or more fine-grained. So the first thing, I want you to become familiar with the way I denote functions, or functions are denoted in math, let's say. So basically to get you familiar with this kind of writing. Then while we are at it, we can talk about the exponential and the logarithmic function, which is of course important because we here have the exponential function, and when we later talk about maximum likelihood estimation, we also need the logarithm. Then we and then we have to fill in some stuff that we didn't talk about in linear algebra previously. Because we have things like that here. So we have a matrix inverse. So we have a matrix inverse that we have to at least touch upon. Then we have transposition here. So this T. So we should briefly talk about transposition, sorry, not transposition, transposition. I realize that I always write probabilistic wrong. In my videos anyway, or in these classes, which are also videos. And 5, we need to talk about actually this thing here, which is the determinant. So I have to briefly remind you of what determinants are. So that actually this formula or equation that you see here, it's not really an equation, it's more formula, that at least you know what the ingredients are, and maybe you have some idea of how these ingredients interact. So that's basically the first plan for the first hour, essentially, I hope, not longer. And then the second is to look at special cases of the multivariate Gaussian, so to look at univariate and bivariate from a intuitive sampling perspective. Bivariate Gaussians. Okay, so that's the plan. Any objections to the plan? No. Good. Okay, so the first thing, functions. I don't think in this course I have talked about the general way that I denote functions. You have all this material that we are covering in this first hour, so that's all in kind of the in the preliminary sections, but we haven't talked about it. So maybe you read it, maybe you didn't, I don't know. So functions. So the functions, of course, you have seen functions in school, so you have seen something like x squared. Not sure whether did I talk about in neurocognitive methods about functions? I don't remember. So you've seen functions, and what you usually did is in school that you had some values on the x-axis and you had some values on kind of the y-axis, and then you evaluated some function, which often you called also y equals x squared, and you plotted it. And I hope you also computed derivatives or something. Yeah. So who has plotted such a function in school? Okay, everybody did that. That's good. The thing that I introduce as essentially just additional notation, but notation that is fairly helpful, and that is a kind of mathematical notation. So it's really something that is specific more to mathematics than to applied fields like physics or so, is to, if a function is defined to be fairly specific about its inputs and its outputs, and also clearly dissociate a function from values that a function takes on. So the general notation that I always use to denote functions is the following. So first of all, there is the function f, by itself. So a function as an abstract rule or abstract rule that takes inputs and returns outputs. Yeah. So and this abstract rule is just the symbol f for the function. Then the way to write functions is then to specify the domain. So let's maybe do it like this. That's not the explanation. That's the domain. So that is the set, and we talked about sets, of all elements that the function can take as input values. Yeah. And then what a function does is take values or elements of its domain, so input values, and map them onto values in its range. So that is the set of output values. Of possible output values, I should say. It's not necessarily the case that all possible output values are actually taken by a function. Why do I think that is important? And here we can immediately go back to our multivariate Gaussian, because it tells you something about this function. So here you say CF, so I call F, with this mu and sigma we'll talk about later, but here is a function that takes on n-dimensional vectors or n-dimensional or lists of real numbers, so lists with m members. So like we talked about r to the power of n, so these are these lists with n elements, which are the real number, and it returns real numbers that are larger than 0. Yeah, so it tells you quite a lot already. So it tells you that it uses that as input you can give it a multivariate or a vector. You can give it a list of n values, and what you get back is only a single value. So that tells you already something. So in this case here, the values that you can put in are real numbers, and the values that you get out are real numbers, although not all real numbers that are possible do you actually get as an output here, because you only get positive or 0 for the x squared. Yeah, so that's something that is especially helpful if you are starting to program, because if you are programming, you also specify functions all the time, and it's really helpful to think about what the inputs are and what the outputs are and what you actually want to solve with your function. So this is something that I like a lot, because at first it helps structuring your thinking, so you know what you're dealing with, and it also helps towards programming. So that's the usual way that I will write it, and then one uses this to express the following. So x is now an element of the range. So of the domain. Jesus, x is an element of the domain. So this is essentially just there to give a label to the elements of the domain. And then this arrow, which looks a little bit different from this arrow, says an element of the domain is mapped onto an element of the range, so a value of the function, and this value of the function is denoted by fx. Yeah, so that's value of f, looks different, of f at x. And that's fairly important to dissociate that this is always a value that the function can take on. So that's, for example, a real number, or in our case, a real number that is larger than 0 for the multivariate Gaussian. And that this is the abstract rule. So this is really helpful if you're specifically if you're looking into differential calculus and so on, so that you can clearly talk about, do I mean a value of the function that it can take on, or do I mean the function itself? So that might not readily apparent from today, but you will see if you go a little bit into actually manipulating these things, that this is really helpful. And then the last thing that needs to be done to specify a function is, of course, to, yeah?
If there is something on the other side of the function, does that mean that we're talking about the function itself?
I don't know what you mean by on the other side.
Sorry, like if it was f of x is defined as x squared?
Yeah, I wasn't finished. So this is actually the last thing that needs to happen, is that this value of the function is usually defined in terms of an element of the domain. So, for example, x squared. Yeah. So what this says is that a value of the function is defined as the square of an input argument. But of course, it can be anything. It can also be, for example, twice x. It can also be x. This function is known as the identity function. So it maps values of its domain onto the same values in its range. Or it can also be independent, if you wish, of the value of x, so be a constant function. But this is really necessary. So this is just a label or denotation for the value of a function, and this is actually what the function takes on as values. Yeah, and this I also did up here. So here I said so x, which you now know is an n-dimensional list of real numbers, or an n-dimensional vector. You all also know that a value of the function is a real number larger than 0, because that was specified here. And this value is here defined in terms of this abbreviation. And this abbreviation is actually then explained here. And you see that the x plays a role. So actually for this function, the x has an effect on the output value, which is the usual case, unless it's a constant function. But there are other entities involved, for example, this mu and this sigma. And I will, so I will always write functions like that. There is not, so one can always, so this function notation is really just a tool so that you can formulate things. And there is usually not the one right way to write a function, but if you want to emphasize something, then it's a good way to be clear about what you want to emphasize and what you're dealing with. Yeah, questions about this notation at this point? I mean, you will see many examples now over the course. Okay, so no questions about this right now. Then let's look briefly at two functions that we will actually, or that are in the probability density function. The first thing is the exponential function. Oops. So one can write that as follows: x, which is now the label for this function, takes in real numbers, and its range are also real numbers, although the values that are actually taken on are strictly positive, as we will see in the graph in a second. Now we label the input arguments. So x is mapped onto x, which you have also seen previously as e to the power of x. Yeah. So e is Euler's number. So e is 2.71 and so on. And that you have seen maybe in school, like e to the power of x. I will usually write this as exp in brackets with the x, because if you have these fairly long expressions as a power, then it gets a little bit annoying. There is actually a definition of this, which is not this, we have a number that we can't really write out. The real definition of the exponential function, which also explains all its properties, is actually a mathematical object that we will not talk about, so it's a little bit pointless to write that out here. So it's a series, so it's an infinite sum of terms, x to the power of n and n factorial. So it's something like 1 plus x squared divided by factor 2 and so on. So that's very interesting, and one can use in math to actually derive all the properties of the exponential function, but it will not be interesting for us, and we will not do that because that would mean that we first have to talk about sequences and series, and we don't want to do that because we don't have that much time. What is most important from our perspective here is that you somehow remember some important facts about the exponential function. So one thing is that x0 is 1. And that essentially the values, how do I write that here? The values of the exponential function are always larger. That's a good way to write it. The values of the exponential functions are, that's on the negative line. No, that's for everything. So exponential, no, that's only for the negative line. So, what is this? So essentially, this says that all the values of the exponential function are positive, and that it goes through this value here. If this is 1, so let's draw 1 here. And then actually the important thing is that you, in a way, have this graph in your head when you think about the exponential function. So that's essentially how it looks. Yeah. So it's always positive. So if you go to a negative number, you still get a positive, but it's getting smaller and smaller and smaller. If you put in 0, you get 1. And if you go above 0, it increases quite fast. Yeah. That's basically as much as we need about the specific stuff. I mean, we will, on occasion, we will always look at maybe some more detailed features of the exponential function. One thing I want to point out here already is, so I'm not talking about exponentiation today, but you will find a little bit on that also in the script. You might recall something like if you have, let's say, 2 to the power of 2 times 2 to the power of 3. How can you also write this? Yeah, 2 to the power of 5. So you can add these, because if you write it out, then you have 2 times 2 times 2 times 2 times 2, which is obviously 2 to the power of 5. And this logic also applies to the exponential function, which means that if you have, for example, if you now write it with the to the power of way, if we have e to the power of a times e to the power of b, this actually evaluates to e to the power of a plus b, and just rewritten in terms of the other way to write the exponential function, this of course corresponds to this, a plus b. And we will need that when we talk a little bit more in detail about the probability density, the Gaussian probability density function, how it relates to independent random variables. Good. Yeah. Maybe do we really need this now? No, we don't really need the logarithm today. So maybe have a look at the logarithm it's essentially, oh wait, now that I mentioned it, so let's briefly talk about logarithm. Logarithm. So essentially, it's defined. So now I'm doing this much less formal. So I essentially one can the logarithm is defined as the inverse function of the exponential function. So basically, what you have is if you apply doesn't go away. We don't have time for this. Doesn't go away anymore. Anyway, if you have the following, if you have the exponential of x and you apply the logarithm, then you get back x. Yeah. The logarithm, you might remember, or also not, that the logarithm of 1 equals 0. So you can, if you plot it, for example, also in here, let's use green. If you here have 1 on the x-axis, then the logarithm looks something like this. For those who do utility functions, for those who do decision neuroscience, that's of course the same logarithm as we use for utility functions in the other course. It goes to negative values as it goes to 0, and then it in a way levels off, but still increases. So it's monotonically increasing here. One important property that we will need from the logarithm, and I will then just bring up again, is that it kind of works against, or it takes operations to lower order, if you know what I mean. And I guess not. What I mean by that is that if you have something like a to the power of b, so an exponentiation property, if you take the logarithm of that, so logarithm a b is b times ln a, so you get rid of the power. And the same thing if you have something like a times b, then the logarithm of a times b is the logarithm of a plus the logarithm of b. So it's fairly useful if you're trying to simplify things, because you get rid of, turn, for example, products into sums and exponentiation into products. That's fairly useful, and we will make use of that. Yeah, I think that's as much as I want to say about exponential function and logarithm. So we will make use of that at a couple of times, and so I just encourage you to look at again at the properties of these functions. It's nothing to really understand about them. It's just that they are entities that have certain properties, and these properties are interesting and can be useful. If you want to understand how these properties arise, though, then you have to go into the mathematical proofs that are definitely beyond the aims of this course. So why do we talk about the exponential function at length? Because we have it here. And actually, we can already, based on this, make at least a little bit, have a little bit of an idea what's happening here. So it gets in, well, you don't know that it's a square yet. So for the moment, it doesn't tell you too much, but at least you know, so at least this exponential function. So you know two things. One thing is, an exponential function is always only defined for a real value, yeah? So that means that this complex thing that you see here must be just a single number. Otherwise, it wouldn't make sense to write something like that. Yeah. So somehow all of this that is in here can be collapsed to a single scalar number. Yeah. So that's something you know, and then you know that it returns positive values, which in a way makes sense because you know that this is supposed to be positive. So at least the definition makes some sense in this regard. One thing that I'm not talking about, and while we are at it, what you also see in the equation are numbers to the power of 1/2. So does anyone remember what a number to the power of 1/2 is?
The square root.
Yep. Exactly. So that's the square root of a number. And something to the power of n over 1/2.
Yes.
Yeah. So the nth square root. The nth root. Yeah. Yeah. The nth root. Let's call it the nth root. So you basically can go. So you roots. I hope you're somewhat familiar with, and then you can roots. You can the inverse of these are squares and higher powers. So that's something. If you're surprised by that, maybe have a brief look at that again. In a way, there's not that much you can learn about this. It's just a definition. One other thing that I'm also not talking about is to the power of minus something. So what is 2 to the power of minus n?
1 over
Hmm?
1 over n? No, 2 times 1. 1 over 2 to the n.
Exactly. I think there was one more combination. Yeah, that's 1 to the 1 over 2 to the power of n. So this minus sign basically puts it into the denominator, the thing. And of course, these things play a role here and here. So what this says is essentially that you should take the square root of 1 over whatever that is here. And this says you should take 2 pi. Pi is just 3.14 and divide 1 by the n squares n. And that's actually quite hard to express in any other word. So it says something like you should do this and take this to the power of n over 2. Yeah. One thing that, now you don't know that yet because you don't know what that is. But at least this thing also doesn't get negative because it's 2 pi and you take it to the power of something. So no negativity comes in here. Good. So these exponentiation, there's a little bit, like I said, there's a little bit on exponentiation in the script, but please look at that in your spare time. Sorry, I know that you have to prepare a lot of papers. Good. Then we talked about functions and we talked about the exponential and logarithm. So there are some things left that we need to talk about, which are from matrix algebra, and they relate to this to the power of -1, which is of course fairly closely related to what we just talked about, but it's for matrix transposition and determinants. So let's maybe get transposition out of the way first. So this is now we're switching essentially mathematical disciplines. So we are now leaving We're now leaving analysis and going into linear algebra. So we previously discussed things like these writings, so that we have something that is, for example, an n-dimensional list and has one column. So you know that what you should think of then is that X has somehow this shape with these entries, which are all real numbers, or maybe a little bit more advanced, that you have this times this, so a real, or not a real matrix, but a matrix where you have rows which are n-dimensional things. So let's, I don't want to write it up, but I do it anyway. 1 n y n 1 y n n. And now one thing we haven't discussed previously was the notion of transposition. And that's fairly easy and very intuitive. So to transpose a matrix or vector means to exchange the rows and columns. So if you transpose, for example, a vector, so if you write x t, so the transpose of x has the same entries as x, but arranged differently, namely in this case as a row, yeah, because this was a column, so this was going down like this, and this looks like this. So just as a little example, so if x is 1, 2, 3, then the transpose of x is 1, 2, 3. Yeah, so that's the transpose. For a vector, for a matrix, it does the same thing. Do I want to rewrite that? It's essentially takes, if this is, so one could write, if one now introduces some notation for columns, then one could write that formally, but I don't want to do that now. So essentially what you need to do to transpose the thing is to take this column and write it up as the first row of the new matrix. And then if you take the second column and use it as the second row of the matrix. And because it's so easy, I think it's better to do that by example. So let's do, that's a good example. 5, 6, 7, 8, 9. Now we want to transpose this matrix Y. So what is its first row? 1, 4, 7. So the first column is now the first row. What's the second row? 0. And the last one? 0. So that's just transposition. And that's really just transposition. Yeah. So there is not much to.
What does T represent?
It's the symbol that says the transpose of y. Yeah. So if y is defined like this, then transpose of y is defined like is equal to this. Yeah? Evaluates as this.
Can T or can T be a different variable?
No, t is just a symbol. T is like plus or times, something like that. Yeah. So it's not a variable. Sometimes it's also denoted by just a bar. But I don't use that. So in linear algebra, it's usually a T for transposition.
Is transposition always something that happens within a single matrix?
Yeah. So yes and no. I mean, you can transpose, for example, matrix products. So, but so you can transpose a matrix product like this. Actually evaluates to the transpose of B times the transpose of A in this reversed order. But of course, in here, there's a single matrix which is given as the product of A and B. So it applies to, in this sense, to single matrices. Cool. Good. So that's transposition. And this we also see in our little equation here. So we see here, let's actually have a closer look at that, because we have what we see here. We for now ignore this sigma to the power of -1 because we don't know what that is. So then it makes sense to ignore it. And what we see here is a transpose, and here we see something like this. So what does that actually mean? Now, I haven't told you what mu is, but in a way you can infer what mu is. So x is, like I told you, an n-dimensional vector. To make this a meaningful statement, x minus mu, what does mu have to be? Exactly. So it needs to be also n-dimensional, otherwise it would be, if it wasn't, then what I wrote up wouldn't make sense, because you know that for matrix addition and subtraction, you need entities to have the same dimensionality or size. So if one computes x minus mu, what do you get out of that? So let's call that, maybe let's call that Z. Let's call that Z. So what do you know about Z? What is Z? Z's dead, baby. Z's dead. Now that's something completely different. Yeah. Also has to be an n-dimensional vector, because x minus, both of them are n-dimensional vectors. You subtract something, you get z. Now then we can, in this expression, this x minus mu t, x minus mu, we can now, because we just called x minus mu, we just called it z. So what we actually have here is z transpose times z. Yeah. And the intuition you should get, this is also called the dot product of two vectors. The intuition you should always get from that is something like z square. Now, why is that the case? And let's have a look why that is a good intuition. So z is an n-dimensional vector, so it looks something like this. And what this thing tells us is that we should transpose z, so we get z, z2, zn times z1, z2, oops, now I'm getting a little bit large here, zn. And what is that? So this is a matrix product, of course. I mean, we're not leaving here the matrix calculus. So what do I have to write on the right side here? On the right side, just do the matrix product. You are doing it in your head, or at least. Yeah.
We have to multiply this row to row.
So if you multiply, and what happens then? What do you get? So what do you multiply? What's your first product?
Z1 to Z1, then plus.
And Z, so then it goes on times Zn, Zn. And then you, of course, know that Z1 is times Z1 is Z squared. This is also Z squared, and it goes on like that, and it's also squared here. And then we can write that a little bit easier in terms of using the sum sign. So we got from I from 1 to n, so we use this index, and we compute the sum over all the zi squared. Yeah, so that's just expressing basically this what is called dot product, so a row vector times a column vector in terms of the sum symbol. And what you see, and this is now somewhat important, is that you see that you add up the squares of n numbers. Now you know that a square is always 0 or positive. So if you square minus 1, what do you get? 1. Yeah. And minus 4? Exactly. So you always get positive numbers if you square 0. Yeah. So you know all of that. That's good. Which means that now if we ignore our sigma to the power of minus 1, which we do for the moment, then this expression here is always larger or equal to 0. Yeah. So this is always positive. Now there's a minus sign in front. There's actually 1/2 in front, but there's also a minus sign in front. So that means that the argument of the exponential function here is always negative. Which then essentially means that we are with our oops, where are we? With our exponential function, we are always in this part. So the input that the exponential function gets in the multivariate Gaussian probability density function is always negative. So we're always in this part, and its maximum value is attained if the input is actually 0. Yeah? So if everything is 0, then we get the maximum value 1, which is not the maximum value of the multivariate Gaussian probability density function because there's something in front, but at least the part that is dependent on x. So this part here is clearly dependent on x because you have the x here and the x here, and this is not dependent on x. This part gets its maximum value at 0, and we will need that again. Okay, so that does that. So then let's have a break now, if there are no other questions right now. No. And then let's clarify after the break the remaining terms, and then talk after that about what kind of intuition that conveys.